So in this second half of Ray's and my talk, I'm going to focus on what we have learned so far from LIGO's observations and on our expectations and our vision for the future. Now I just have to figure out this slide. Okay, good. But before I begin, Ray and I want to acknowledge the superb team and collaborations that have made LIGO discoveries possible. LIGO began in the early 1980s as a collaboration between Caltech and MIT and the U.S. National Science Foundation, and for their strong institutional support, we're very grateful. The U.S. Congress made its first big investment of taxpayer money in LIGO in 1992, and from then until now, thanks to vigorous support from NSF and NSF directors such as Rita Caldwell, who is here today, thanks to their support, Congress has backed us unwaveringly, independent of which political party was in power, allocating $1.1 billion to our quest. For this and for the enthusiasm of so many of the American people, we're also very grateful. As Ray has described, in the 1990s, Barry Barish led us in creating the modern LIGO project, which consists of two entities. The first is the LIGO laboratory, which is responsible for the R&D that led to the advanced LIGO interferometers that have detected the gravitational waves and is responsible for operating the interferometers. I'm going to show you photos of many of the LIGO lab's superb scientists and engineers. First, the ones at the Caltech site, those at MIT, those at the LIGO Livingston Observatory, and those at the LIGO Hanford Observatory. The second entity in the modern LIGO structure is the LIGO Scientific Collaboration, which is responsible for organizing and coordinating LIGO's technical and scientific research, including the analyses that led to the discovery of the gravitational waves in LIGO's noisy data. This is a collaboration of about 1,000 scientists in 80 institutions in 16 nations. And as Ray has mentioned, and I shall describe a bit more shortly, there's a third advanced gravitational wave detector that is going to go online within the next year called Virgo, that's just beginning to operate. The Virgo collaboration includes scientists, several hundred scientists and engineers from Italy, France, the Netherlands, Poland, and Spain. And the Virgo scientists contributed to the data analysis of the LIGO data that make the discovery. So the discovery was a joint LIGO-Virgo discovery. Ray Weiss, Ron Drever, and I, as the founders of the LIGO collaboration and project, as founders of the LIGO project, get a lot more credit than we deserve. The greatest credit for LIGO's discovery should go, in fact, to the superb scientists and engineers who made these interferometers work. Put them together and made them work in the end. And the members of the LIGO-Virgo collaboration who found the data, the signals in the data and extracted the information the signals were carrying. Now, Advanced LIGO's first search for gravitational waves lasted from September 12 of last year until January 19th. The results are now available on the web, on the Physics Archive, as the publication number 1606.04856. This is not yet published, but it's in the public domain. And in those that search, that 4-month search, the LIGO-Virgo collaborators found 3 gravitational wave signals. One is well known, the other 2 are not so well known. I'm showing here those 3 signals initially plotted on the noise curve that Ray showed you. This is the actual noise curve at the time that the signals came in. Frequency from 10 hertz to 1,000 hertz, and the noise in the strain per root hertz, going from 10 to the minus 23 to 10 to the minus 22, and the signals superimposed on this. The blue signal was the first one that came in, and it swept upward in frequency, entering the LIGO frequency band at 30 hertz frequency, and then dying quickly when it reached 240 hertz. Here you see the actual waveform during that period from 30 hertz to 240 hertz, very short, but very strong waves, so strong, as Ray has shown you, that it could be seen by eye. And the actual strain, as Ray remarked, was 10 to the minus 21, which is really a magical number, because in 1978, when we were just starting to get going, before we had created the LIGO collaboration between Caltech and MIT, we had a workshop of all the people, a very small number of people working in the field at that time. We looked at all the possible sources we might search for with these interferometers and with bar detectors, and concluded that in order to have success, we needed to be able to measure strains of 10 to the minus 21. And 10 to the minus 21 became our goal. We even had T-shirts that said 10 to the minus 21 or bust at the end of this workshop. 10 to the minus 21 was the strength of the first gravitational wave that was seen. And this is rather remarkable in a similar way. Already by the early 1980s, we knew what sources we were going after, and our ideas as to what we're likely to see have not changed a great deal since then. And the fundamental reason is that our current knowledge of the universe comes largely from electromagnetic waves, and they are so different from gravitational waves that they have not taught us a whole lot about what we're going to see in those intervening decades. Now it's a whole new ballgame. We're beginning to see it, and there are going to be some wonderful discoveries as we go on. The second, so I talked about the blue signal. Let me go on. I'm pushing on the wrong button. Here we go. The second signal that was found is shown here in green. It's called LVT 151012 because it came in on October 12. It's a much weaker signal than our first signal. It entered LIGO's frequency band at about 40 hertz. It chirped upward in frequency to about 400 hertz, and then it died out quickly. To find this signal, the LIGO scientists had to dig very deep into the noise using the technique that Ray described of matching the theoretical templates that were deduced by theorists for what should come from merging black holes, for beating those against the noisy LIGO data. The signal, in fact, was so weak that we're only 87% sure that this green signal was the real thing. But 87% is good enough that we take it quite seriously. It has all the hallmarks of being the real thing. The third signal, shown in brown, called GW1526, arrived on Boxing Day in the UK. It was actually Christmas Day in America, the great Christmas present that nature gave to us. That signal swept into the LIGO band at about 35 hertz. It swept upward in frequency to about 800 hertz and then died quickly. It was strong enough to be an ironclad detection like the first one, but so weak that it could only be found by digging deep into the noise. And you see it was a very, very, very long signal by contrast with this one. And the reason is that this was a much less massive system. So it did not sweep nearly so rapidly upward in frequency as the first one that we saw. In order to find these second and third signals, we had to use a template bank of highly reliable gravitational waveforms that were produced, that would be produced by merging black holes. For these waveforms, we relied on solutions of Einstein's general relativity equations that came from the combined work of a huge number of theoretical physicists who were not at all associated with the LIGO project. At low frequencies, as the black holes were going around each other, moving in until they reached about 1/3 of the speed of light, when this method failed, the calculations were done by a perturbative expansion called the Post-Newtonian Method, in which Einstein's equations were solved order by order up to the 7th power of the velocity, orbital velocity, in powers of the orbital velocity. This was a tour de force carried out by something like 30 people over a period of 40 years, one of the earliest being Subramanian Chandrasekhar. This led by 2000 to having waveforms for the early parts of these inspiral signals that were very reliable, good enough for LIGO's data analysis. For the period after the orbital speeds reached 1/3 the speed of light in the collision, the only way that we have to solve Einstein's equations is through computer simulations. And so that was a 50-year effort, developing the tools, the techniques, and perfecting them for computer simulations by 150 people over a 50-year, in parallel with basically hand in hand with the work of the LIGO project. Again, these are people, computational physicists, who are not in any way associated with the LIGO project. So this discovery really is the product not only of the LIGO scientists, the Virgo scientists, but of several other communities of theorists who gave major contributions that were absolutely essential. By September of 2015, several numerical relativity groups had the capability to simulate generic binary black holes. Here is a simulation in the case of two black holes, one 60 times heavier than the sun, spinning at 91% of the fastest speed that a black hole can spin at, and a 10 solar mass black hole at 30% of the fastest speed with randomly oriented spin directions. And the waveforms are much more complicated and much more interesting than what you saw from the first three LIGO detections. We do expect to see things that are more complicated like this, more interesting like this, and they will tell us new things that we've not yet seen about the dynamics of warp space and time. To learn the source's details, once the waves had been discovered, we went in then and compared advanced LIGO's observed waveforms with the waveforms that came from computer simulations. And from those comparisons, we deduced the masses of the black holes. For the first signal, a 36 solar mass black hole, a 29 solar mass black hole, merging to form a 62 solar mass black hole, and releasing 3 solar masses of energy in gravitational waves. It's as though 3 suns had been annihilated and turned all into gravitational wave energy. And that was done so quickly that the power output, the energy per unit time, during the collision, a small fraction of a second, the power output was 50 times larger than the total luminosity of all the stars in the universe put together. 50 universal luminosities coming off of 2 colliding black holes, no electromagnetic waves at all. And this illustrates the importance of gravitational wave astronomy. We begin now to study things that you cannot study using electromagnetic waves, aspects of the universe that I like to call the warped side of the universe, that are a whole new ball game, whole new insights on the universe we live in. The second signal was much smaller masses, 23 solar masses and 13 solar masses, with 1.5 solar mass coming off in gravitational waves at a distance of 3 billion light years compared to 1.3 billion light years. So the smaller masses and the greater distance is why the signal was much weaker. The third one, 14 solar masses, yes, still smaller yet, and 8 solar masses, but closer than the second one, 1.4 billion light years, which made it that plus the fact we had so many more cycles in order to build up the signal in the data analysis enabled this to be an ironclad detection. So we also then learned what the black holes were doing during these collisions from the simulations, and in particular by making videos of what they were doing. And so here I'm going to show you a video made by 3 graduate students at Cornell University, Andy Bohn, Francois Hébert, and Will Throw, based on simulations of the first gravitational wave detection done by the SXS collaboration, which is Caltech, Cornell, and the Canadian Institute for Theoretical Astrophysics in Toronto. What you are seeing is what this would have looked like. Is it possible to turn the lights down up here? This is what it would look like to your eyes as these 2 black holes, these are the black shadows here, go around each other, gravitational lensing a star field that's behind them. And so this is just a sort of a more or less uniform star field, but the light rays go around the black holes and come to your eyes, having been bent in such a way as to make a remarkable pattern, make a remarkable pattern as the 2 black holes go around each other. So they're orbiting around and around. And this region out here that is so interesting is what is called the Einstein ring. It is common in gravitational lensing. And the one black hole is a little smaller than the other black hole, and they are about to merge. They merged, and 3 solar masses of gravitational wave energy came off, but it was not all that impressive to your eyes. In order to see it be really impressive, you need to see the warped space and warped time. And we can do that by imagining that we look in from a higher dimensional space onto our universe. For those of you who saw the movie Interstellar that I had some role in, you're looking in from the fifth dimension of the movie Interstellar. For a physicist, this is basically an embedding diagram of the shape of space of the binary black hole system during the merger. So each black hole, then, as you look in, you're seeing a slice through the orbital plane of the black hole. Each black hole makes a funnel down here, and so that's the shape of space, the funnels. The silver arrows are the dragging of space into motion by the orbital motion of the black holes and by the gravity of the black holes. And the colors are the slowing of time near the black holes. And we're going to watch the black holes now as they orbit around each other. And I'm going to slow it down as they begin to merge. So this is going into slow motion. And this is now a storm in the fabric of space and time being created like waves in the ocean in a violent storm. That's the moment of collision, enormous distortion of space, enormous slowing of time as color-coded by the red colors. And now it's settled back down, a single black hole, and the gravitational waves are going away. The collision created, indeed, a veritable storm in the fabric of space and time, which was responsible for emitting the 3 solar masses of energy so quickly. How often do black holes collide? Well, we now know from these observations, roughly once per month at LIGO's current sensitivity, but we're at about a third of design sensitivity. By 2019, we will be seeing 3 times farther, so the volume of the universe that we can see will be 3 cubed or 27 times larger. We should be seeing a few per week, or maybe even 1 per day. In terms of absolute numbers, from the observations we have, in a region of 1 billion light years on a side, there's about 1 to 20 black hole collisions per year. In the observable universe, that extrapolates to at least a few per hour, and maybe much more than that, because in the earlier universe, the conditions were quite different. We don't yet see all the way back to the earlier universe, and so we can't say how common they were in the earlier universe. Where on the sky were these colliding black holes? Well, we get the directionality by the delay in the time of arrival of the signals at the different sites. And so we have the first signal came in somewhere on the sky above this location down there in Antarctica. The gravitational waves entered the Earth down near the South Pole, traveled through the Earth, and emerged first at the Livingston site, and then 7 milliseconds later at the Hanford site, having been totally unscathed by passing through the Earth. The others are less well localized because the signals were weaker. This is lousy localization if you want to ask an electromagnetic astronomer to look for a coincident electromagnetic signal. So it's really crucial to us for getting better directions that we have more gravitational wave detectors. And so we do have now LIGO Hanford, LIGO Livingston. We have the Virgo detector go into operation sometime within the next year. The Kagra detector in Japan, which should go into operation around 2019. And we are putting a LIGO detector in India going into operation around 2022. And by that time, we will then be able to get error boxes on the sky that are getting down to nearly as small as the moon is. And that is an enormous boon to electromagnetic astronomers who want to look for X-rays, gamma rays, optical radiation coming from the same source. What else will advanced LIGO see? We're going to see gravitational waves from spinning neutron stars, from black holes tearing neutron stars apart, from colliding neutron stars. Each of these neutron stars, of course, as Ray remarked, is the size of Oslo. The density, 10 times the density of an atomic nucleus. From these collisions and from tearing a neutron star apart by a black hole, we will learn a lot about the properties of the nuclear matter, supernuclear matter, of which the neutron stars are made. We hope to see the cores of supernova explosions, thereby learn really what goes on down in the core. And cosmic strings. These are things somewhat like fundamental strings that are thought to be the building blocks of all matter, except they're gigantic. They stretch across the universe, and they are thought to have been made in the various earliest moments of the universe through fundamental physics processes. We will have big surprises. And with most of these sources, we'll have electromagnetic counterparts, so we will be doing multi-messenger astronomy, different messengers being gravitational waves, X-rays, light, radio waves, and so forth. We will move beyond advanced LIGO. Advanced LIGO should reach its design sensitivity in 2019. There are tentative plans on the drawing boards for a third generation of detectors in these same vacuum systems, so with arm lengths of 4 kilometers, to operate in the late 2020s. 3 times better sensitivity, and another factor of 27 bigger volume of the universe. And then tentative plans for the following generation, say in the late 2030s, that may have 40-kilometer arms, whole new vacuum system, 40-kilometer arms, another factor of 4 in sensitivity, or 4 cubed, in the volume of the universe that we searched through. So this is really a very exciting future in that sense. I was going to talk a little bit about LIGO's amazing technology. I'll show you one slide on that because I'm running out of time. Advanced LIGO in 2019 will be monitoring the motions of 40-kilogram mirrors to an accuracy of 10 to the minus 19 meters. That is approximately the half of the width of the Schrodinger wave function of the center of mass degree of freedom of our mirrors. That means that for the first time we will be seeing human-sized objects behave quantum mechanically with quantum fluctuations in the location of the mirrors that we have to deal with in the data analysis and have them not get in the way of the measurements. In the third generation, we will be making measurements at the level of 1/6 of the wave function, of the width of a wave function, digging deep down into the quantum noise that is associated with a 40-kilogram mirror behaving like a 40-kilogram particle governed by the laws of quantum theory and not by the laws of classical physics. For the first time then, as I said, humans will see human-sized objects behave quantum mechanically. This was predicted in 1968 by Vladimir Braginsky, a dear colleague of ours in Moscow, Russia, who told us, for this field to succeed, you have to deal with this phenomenon, macroscopic quantum mechanics of your detectors. The quantum non-demolition technology to deal with this has been developed. By quantum non-demolition, I mean that you get a highly classical gravitational wave signal going through a quantum mechanical detector, 40-kilogram quantum particles, unscathed. You make the output, thereby you make the output insensitive to the quantum state of the mirrors. The gravitational wave signal is not demolished by the quantum behavior of the system, and that's what we mean by quantum non-demolition. I'm now going to skip through a whole bunch of stuff, and I just want to wind up with this was just how we do that. But I want to wind up by saying that LIGO is just the first of the gravitational wave windows that we are going to have in the next 20 years. LIGO looks for gravitational waves with oscillations of periods of milliseconds. There will be a detector called LISA that is currently an all-European mission. We are hoping that NASA will join with ESA to make this a more robust mission, likely to fly around 2030 or shortly thereafter. It involves spacecraft that track each other with laser beams and looking for gravitational waves with periods of minutes to hours. There is a technique involving a timing of pulsars, timing of array of pulsars. The gravitational wave sweeps across the Earth. It speeds up and slows down our clocks. As a result, it makes it appear that the pulses coming from pulsars at different locations in the sky arrive with fluctuating time separations that fluctuate in synchrony between all these sources. And then there's a technique looking for a pattern polarization of cosmic microwave background on the sky that looks for gravitational waves from the earliest moments of the universe. So that by the second half of the 21st century, we will have 4 different frequency bands that we're operating at, and the most interesting things we will be doing is exploring the first 1 second of our universe's life. We'll be looking for gravitational waves, primordial, that were created at the earliest moment of the universe and amplified through a phenomenon called inflation. We'll be looking for waves from first-order phase transitions, watching the birth of the electromagnetic force, watching the birth of fundamental forces at the beginning of the universe. Waves from cosmic strings that I mentioned, domain walls, perhaps even waves from oscillations of our universe as a membrane living in a higher dimensional universe. So the gravitational waves are going to be a major tool for astronomy, not just in the next few years, the next few decades, but into the next century and beyond. And astronomy is going to look very different as a result of this new technology than it does look today. Thank you.